Make a close examination for rivets that have partially failed and for holes that have been elongated. Whether specific damage is suspected or not, an aircraft structure must occasionally be inspected for structural integrity. The following paragraphs provide general guidelines for this inspection. When inspecting the structure of an aircraft, it is very important to watch for evidence of corrosion on the inside. This is most likely to occur in pockets and corners where moisture and salt spray may accumulate, therefore, drain holes must always be kept clean. While an injury to the skin covering caused by impact with an object is plainly evident, a defect, such as distortion or failure of the substructure, may not be apparent until some evidence develops on the surface, such as canted, buckled or wrinkled covering, and loose rivets or working rivets. A working rivet is one that has movement under structural stress, but has not loosened to the extent that movement can be observed. This situation can sometimes be noted by a dark, greasy residue or deterioration of paint and primers around rivet heads. External indications of internal injury must be watched for and correctly interpreted. When found, an investigation of the substructure in the vicinity should be made and corrective action taken. Warped wings are usually indicated by the presence of parallel skin wrinkles running diagonally across the wings and extending over a major area. This condition may develop from unusually violent maneuvers, extremely rough air, or extra hard landings. While there may be no actual rupture of any part of the structure, it may be distorted and weakened. Similar failures may also occur in fuselages. Small cracks in the skin covering may be caused by vibration, and they are frequently found leading away from rivets. Aluminum alloy surfaces having chipped protective coating, scratches, or worn spots that expose the surface of the metal should be recoated once, as corrosion may develop rapidly. The same principle is applied to aluminum-clad, alclad surfaces. Scratches, which penetrate the pure aluminum surface layer, permit corrosion to take place in the alloy beneath. A simple visual inspection cannot accurately determine if suspected cracks in major structural members actually exist or the full extent of the visible cracks. Eddy current and ultrasonic inspection techniques are used to find hidden damage. Types of damage and defects. Types of damage and defects that may be observed on aircraft parts are defined as follows. 1. Brinelling, occurrence of shallow, spherical depressions in a surface, usually produced by a part having a small radius in contact with the surface under high load. 2. Burnishing, polishing of one surface by sliding contact with a smooth, harder surface. Usually there is no displacement or removal of metal. 3. Burr, a small, thin section of metal extending beyond a regular surface, usually located at a corner or on the edge of a hole. 4. Corrosion, loss of metal from the surface by chemical or electrochemical action. The corrosion products generally are easily removed by mechanical means. Iron rust is an example of corrosion. 5. Crack, a physical separation of two adjacent portions of metal, evidenced by a fine or thin line across the surface caused by excessive stress at that point. It may extend inward from the surface from a few thousandths of an inch to completely through the section thickness. 6. Cut, loss of metal, usually to an appreciable depth over a relatively long and narrow area, by mechanical means, as would occur with the use of a saw blade, chisel, or sharp-edged stone striking a glancing blow. 7. Dent, indentation in a metal surface produced by an object striking with force. The surface surrounding the indentation is usually slightly upset. 8. Erosion, loss of metal from the surface by mechanical action of foreign objects, such as grit or fine sand. The eroded area is rough and may be lined in the direction in which the foreign material moved relative to the surface. 9. Chattering, breakdown or deterioration of metal surface by vibratory or chattering action. Although chattering may give the general appearance of metal loss or surface cracking, usually, neither has occurred. 10. Galling, breakdown, or buildup of metal surfaces due to excessive friction between two parts having relative motion. Particles of the softer metal are torn loose and welded to the harder metal. 11. Gouge, groove in, or breakdown of a metal surface from contact with foreign material under heavy pressure. Usually it indicates metal loss but may be largely the displacement of material. 12. Inclusion, presence of foreign or extraneous material wholly within a portion of metal. Such material is introduced during the manufacture of rod, bar, or tubing by rolling or forging. End of page 4 to 89. 13. Nick, local break or notch on an edge. Usually it involves the displacement of metal rather than loss. 14. Pitting, sharp, localized breakdown, small, deep cavity, of metal surface, usually with defined edges. 15. Scratch, slight tear or break in metal surface from light, momentary contact by foreign material. 16. Scored deeper than scratch, tear or break in metal surface from contact under pressure. May show discoloration from temperature produced by friction. 17. Stain, a change in color, locally causing a noticeably different appearance from the surrounding area. 18. Upsetting, a displacement of material beyond the normal contour or surface, a local bulge or bump. Usually it indicates no metal loss. Classification of damage. Damages may be grouped into 4 general classes. In many cases, the availabilities of repair materials and time are the most important factors in determining if a part should be repaired or replaced. Negligible damage. Negligible damage consists of visually apparent, surface damage that do not affect the structural integrity of the component involved. Negligible damage may be left as is or may be corrected by a simple procedure without restricting flight. In both cases, some corrective action must be taken to keep the damage from spreading. Negligible or minor damage areas must be inspected frequently to ensure the damage does not spread. Permissible limits for negligible damage vary for different components of different aircraft and should be carefully researched on an individual basis. Failure to ensure that damage is within the specified limit of negligible damage may result in insufficient structural strength of the affected support member for critical flight conditions. Small dents, scratches, cracks, and holes that can be repaired by smoothing, sanding, stop drilling, or hammering out, or otherwise repaired without the use of additional materials, fall in this classification. Figure 4, 170. Damage reparable by patching. Damage reparable by patching is any damage exceeding negligible damage limits that can be repaired by installing splice members to bridge the damaged portion of a structural part. The splice members are designed to span the damaged areas and to overlap the existing undamaged surrounding structure. The splice or patch material used in internal riveted and bolted repairs is normally the same type of material as the damaged part, but 1 gauge heavier. In a patch repair, filler plates of the same gauge and type of material as that in the damaged component may be used for bearing purposes or to return the damaged part to its original contour. Structural fasteners are applied to members and the surrounding structure to restore the original load-carrying characteristics of the damaged area. The use of patching depends on the extent of the damage and the accessibility of the component to be repaired. Damage reparable by insertion. Damage must be repaired by insertion when the area is too large to be patched or the structure is arranged such that repair members would interfere with structural alignment, e.g., in a hinge or bulkhead. In this type of repair, the damaged portion is removed from the structure and replaced by a member identical in material and shape. Splice connections at each end of the insertion member provide for load transfer to the original structure. Damage necessitating replacement of parts. Components must be replaced when their location or extent of damage makes repair impractical, when replacement is more economical than repair, or when the damaged part is relatively easy to replace. For example, replacing damaged castings, forgings, hinges, and small structural members, when available, is more practical than repairing them. Some highly stressed members must be replaced because repair would not restore an adequate margin of safety. Repairability of sheet metal structure. The following criteria can be used to help an aircraft technician decide upon the repairability of a sheet metal structure. 1. Type of damage. End of page 4 to 90. 2. Type of original material. 3. Location of the damage. 4. Type of repair required. 5. tools and equipment available to make the repair. The following methods, procedures, and materials are only typical and should not be used as the authority for a repair. Structural support during repair. During repair, the aircraft must be adequately supported to prevent further distortion or damage. It is also important that the structure adjacent to the repair is supported when it is subject to static loads. The aircraft structure can be supported adequately by the landing gear or by jacks where the work involves a repair, such as removing the control surfaces, wing panels, or stabilizers. Cradles must be prepared to hold these components while they are removed from the aircraft. When the work involves extensive repair of the fuselage, landing gear, or wing center section, a jig, a device for holding parts in position to maintain their shape, may be constructed to distribute the loads while repairs are being accomplished. Figure 4.171 shows a typical aircraft jig. Always check the applicable aircraft maintenance manual for specific support requirements. Assessment of damage. Before starting any repair, the extent of damage must be fully evaluated to determine if repair is authorized or even practical. This evaluation should identify the original material used and the type of repair required. The assessment of the damage begins with an inspection of riveted joints and an inspection for corrosion. Inspection of riveted joints. Inspection consists of examining both the shop and manufactured heads and the surrounding skin and structural parts for deformities. During the repair of an aircraft structural part, examine adjacent parts to determine the condition of neighboring rivets. The presence of chipped or cracked paint around the heads may indicate shifted or loose rivets. If the heads are tipped or if rivets are loose, they show up in groups of several consecutive rivets and are probably tipped in the same direction. If heads that appear to be tipped are not in groups and are not tipped in the same direction, tipping may have occurred during some previous installation. Inspect rivets that are known to have been critically loaded, but that show no visible distortion, by drilling off the head and carefully punching out the shank. If upon examination, the shank appears joggled and the holes in the sheet misaligned, the rivet has failed in shear. In that case, determine what is causing the stress and take necessary corrective action. Countersunk rivets that show head slippage within the countersink or dimple, indicating either sheet bearing failure or rivet shear failure, must be replaced. Joggles in removed rivet shanks indicate partial shear failure. Replace these rivets with the next larger size. Also, if the rivet holes show elongation, replace the rivets with the next larger size. Sheet failures, such as tear-outs, cracks between rivets, and the like, usually indicate damaged rivets, and the complete repair of the joint may require replacement of the rivets with the next larger size. The presence of a black residue around the rivets is not an indication of looseness, but it is an indication of movement, fretting. The residue, which is aluminum oxide, is formed by a small amount of relative motion between the rivet and the adjacent surface. This is called fretting corrosion, or smoking, because the aluminum dust quickly forms a dark, dirty-looking trail, like a smoke trail. Sometimes, the thinning of the moving pieces can propagate a crack. If a rivet is suspected of being defective, this residue may be removed with a general-purpose abrasive hand pad, such as those manufactured by Scotch-Brite, and the surface inspected for signs of pitting or cracking. End of page 4-91. Although the condition indicates the component is under significant stress, it does not necessarily precipitate cracking. Figure 4.172. Airframe cracking is not necessarily caused by defective rivets. It is common practice in the industry to size rivet patterns assuming one or more of the rivets is not effective. This means that a loose rivet would not necessarily overload adjacent rivets to the point of cracking. Rivet head cracking is acceptable under the following conditions. 1. The depth of the crack is less than 1/8 of the shank diameter. 2. The width of the crack is less than 1/16 of the shank diameter. 3. The length of the crack is confined to an area on the head within a circle having a maximum diameter of 11/4 times the shank diameter. 4. Cracks should not intersect, which creates the potential for the loss of a portion of a head. Inspection for corrosion. Corrosion is the gradual deterioration of metal due to a chemical or electrochemical reaction with its environment. The reaction can be triggered by the atmosphere, moisture, or other agents. When inspecting the structure of an aircraft, it is important to watch for evidence of corrosion on both the outside and inside. Corrosion on the inside is most likely to occur in pockets and corners where moisture and salt spray may accumulate, therefore, drain holes must always be kept clean. Also inspect the surrounding members for evidence of corrosion. Damage removal. To prepare a damaged area for repair. 1. Remove all distorted skin and structure in damaged area. 2. Remove damaged material so that the edges of the completed repair match existing structure and aircraft lines. 3. Round all square corners. 4. Smooth out any abrasions and/or dents. 5. Remove and incorporate into the new repair any previous repairs joining the area of the new repair. Repair material selection. The repair material must duplicate the strength of the original structure. If an alloy weaker than the original material has to be used, a heavier gauge must be used to give equivalent cross-sectional strength. A lighter gauge material should not be used even when using a stronger alloy. Repair parts layout. All new sections fabricated for repairing or replacing damaged parts in a given aircraft should be carefully laid out to the dimensions listed in the applicable aircraft manual before fitting the parts into the structure. Rivet selection. Normally, the rivet size and material should be the same as the original rivets in the part being repaired. If a rivet hole has been enlarged or deformed, the next larger size rivet must be used after reworking the hole. When this is done, the proper edge distance for the larger rivet must be maintained. Where access to the inside of the structure is impossible and blind rivets must be used in making the repair, always consult the applicable aircraft maintenance manual for the recommended type, size, spacing, and number of rivets needed to replace either the original installed rivets or those that are required for the type of repair being performed. Rivet spacing and edge distance. The rivet pattern for a repair must conform to instructions in the applicable aircraft manual. The existing rivet pattern is used whenever possible. Corrosion treatment. Prior to assembly of repair or replacement parts, make certain that all existing corrosion has been removed in the area and that the parts are properly insulated one from the other. Approval of repair. Once the need for an aircraft repair has been established, Title 14 of the Code of Federal Regulations, 14 CFR, defines the approval process. 14 CFR Part 43, Section 43.13a, states that each person performing maintenance, alteration, or preventive maintenance on an aircraft, engine, propeller, or appliance shall use the methods, techniques, and practices prescribed in the current manufacturer's maintenance manual or instructions for continued airworthiness prepared by its manufacturer, or other methods, techniques, or practices acceptable to the administrator. End of page 4 to 92. AC 43.13-1 contains methods, techniques, and practices acceptable to the administrator for the inspection and repair of non-pressurized areas of civil aircraft, only when there are no manufacturer repair or maintenance instructions. This data generally pertains to minor repairs. The repairs identified in this AC may only be used as a basis for FAA approval for major repairs. The repair data may also be used as approved data, and the AC chapter, page, and paragraph listed in Block 8 of FAA Form 337 when the user has determined that it is appropriate to the product being repaired. B. It is directly applicable to the repair being made, and C. It is not contrary to manufacturer's data. Engineering support from the aircraft manufacturer is required for repair techniques and methods that are not described in the Aircraft Maintenance Manual or SRM. FAA Form 337, Major Repair and Alteration, must be completed for repairs to the following parts of an airframe and repairs of the following types involving the strengthening, reinforcing, splicing, and manufacturing of primary structural members or their replacement, when replacement is by fabrication, such as riveting or welding. Figure 4, 173. 1. Box beams. 2. Monocoque or semi-monocoque wings or control surfaces. 3. Wing stringers or cord members. 4. Spars. 5. Spar flanges. 6. Members of truss-type beams. 7. Thin sheet webs of beams. 8. Keel and chine members of boat hulls or floats. 9. Corrugated sheet compression members that act as flange material of wings or tail surfaces. 10. Wing main ribs and compression members. 11. Wing or tail surface brace struts, fuselage longerons. 12. Members of the side truss, horizontal truss, or bulkheads. 13. Main seat support braces and brackets. 14. Landing gear brace struts. 15. Repairs involving the substitution of material. 16. Repair of damaged areas in metal or plywood stressed. Covering exceeding 6 inches in any direction. 17. Repair of portions of skin sheets by making additional seams. 18. Splicing of thin sheets. 19. Repair of 3 or more adjacent wing or control surface ribs or the leading edge of wings and control surfaces between such adjacent ribs. For major repairs made in accordance with a manual or specifications acceptable to the administrator, a certificated repair station may use the customer's work order upon which the repair is recorded in place of the FAA Form 337. Repair of stressed skin structure. In aircraft construction, stressed skin is a form of construction in which the external covering, skin, of an aircraft carries part or all of the main loads. Stressed skin is made from high-strength rolled aluminum sheets. Stressed skin carries a large portion of the load imposed upon an aircraft structure. Various specific skin areas are classified as highly critical, semi-critical, or non-critical. To determine specific repair requirements for these areas, refer to the applicable aircraft maintenance manual. Minor damage to the outside skin of the aircraft can be repaired by applying a patch to the inside of the damaged sheet. A filler plug must be installed in the hole made by the removal of the damaged skin area. It plugs the hole and forms a smooth outside surface necessary for aerodynamic smoothness of the aircraft. The size and shape of the patch is determined in general by the number of rivets required in the repair. If not otherwise specified, calculate the required number of rivets by using the rivet formula. Make the patch plate of the same material as the original skin and of the same thickness or of the next greater thickness. Patches. Skin patches may be classified as 2 types. 1. Lap or scab patch. 2. Flush patch. Lap or scab patch. The lap or scab type of patch is an external patch where the edges of the patch and the skin overlap each other. The overlapping portion of the patch is riveted to the skin. Lap patches may be used in most areas where aerodynamic smoothness is not important. Figure 4:174 shows a typical patch for a crack and/or for a hole. When repairing cracks or small holes with a lap or scab patch, the damage must be cleaned and smooth. In repairing cracks, a small hole must be drilled in each end and sharp end of the crack before applying the patch. End of page 4 to 93. Figure 4:173. FAA Form 337, Major Repair and Alteration, Airframe, Power Plant, Propeller, or Appliance. End of page 4 to 94. Figure 4:173. FAA Form 337, Major Repair and Alteration, Airframe, Power Plant, Propeller, or Appliance, continued. End of page 4 to 95. These holes relieve the stress at these points and prevent the crack from spreading. The patch must be large enough to install the required number of rivets. It may be cut circular, square, or rectangular. If it is cut square or rectangular, the corners are rounded to a radius no smaller than 1/4 inch. The edges must be chamfered to an angle of 45 degrees for 1/2 the thickness of the material, and bent down 5 degrees over the edge distance to seal the edges. This reduces the chance that the repair is affected by the airflow over it. These dimensions are shown in Figure 4:175. Flush patch. A flush patch is a filler patch that is flush to the skin. When applied, it is supported by and riveted to a reinforcement plate which is, in turn, riveted to the inside of the skin. Figure 4:176 shows a typical flush patch repair. The doubler is inserted through the opening and rotated until it slides in place under the skin. The filler must be of the same gauge and material as the original skin. The doubler should be of material 1 gauge heavier than the skin. End of page 4 to 96. Open and closed skin area repair. The factors that determine the methods to be used in skin repair are accessibility to the damaged area and the instructions found in the Aircraft Maintenance Manual. The skin on most areas of an aircraft is inaccessible for making the repair from the inside and is known as closed skin. Skin that is accessible from both sides is called open skin. Usually, repairs to open skin can be made in the conventional manner using standard rivets, but in repairing closed skin, some type of special fastener must be used. The exact type to be used depends on the type of repair being made and the recommendations of the aircraft manufacturer. Design of a patch for a non-pressurized area. Damage to the aircraft skin in a non-pressurized area can be repaired by a flush patch if a smooth skin surface is required or by an external patch in non-critical areas. Figure 4, 177. The first step is to remove the damage. Cut the damage to a round, oval, or rectangular shape. Round all corners of a rectangular patch to a minimum radius of 0.5 inch. The minimum edge distance used is 2 times the diameter and the rivet spacing is typically between 4 to 6 times the diameter. The size of the doubler depends on the edge distance and rivet spacing. The doubler material is of the same material as the damaged skin, but of one thickness greater than the damaged skin. The size of the doubler depends on the edge distance and rivet spacing. The insert is made of the same material and thickness as the damaged skin. The size and type of rivets should be the same as rivets used for similar joints on the aircraft. The SRM indicates what size and type of rivets to use. Typical repairs for aircraft structures. This section describes typical repairs of the major structural parts of an airplane. When repairing a damaged component or part, consult the applicable section of the manufacturer's SRM for the aircraft. Normally, a similar repair is illustrated, and the types of material, rivets, and rivet spacing and the methods and procedures to be used are listed. Any additional knowledge needed to make a repair is also detailed. If the necessary information is not found in the SRM, attempt to find a similar repair or assembly installed by the manufacturer of the aircraft. Floats. To maintain the float in an airworthy condition, periodic and frequent inspection should be made because of the rapidity of corrosion on metal parts, particularly when the aircraft is operated in salt water. Inspection of floats and hulls involves examination for damage due to corrosion, collision with other objects, hard landings, and other conditions that may lead to failure. Note: blind rivets should not be used on floats or amphibian hulls below the waterline. Sheet metal floats should be repaired using approved practices. However, the seams between sections of sheet metal should be waterproofed with suitable fabric and sealing compound. A float that has undergone hull repairs should be tested by filling it with water and allowing it to stand for at least 24 hours to see if any leaks develop. Figure 4, 178. Corrugated skin repair. Some of the flight controls of smaller general aviation aircraft have beads in their skin panels. The beads give some stiffness to the thin skin panels. The beads for the repair patch can be formed with a rotary former or press brake. Figure 4, 179. Replacement of a panel. Damage to metal aircraft skin that exceeds reparable limits requires replacement of the entire panel. Figure 4, 180. End of page 4 to 97. Figure 4, 178. Float repair. End of page 4 to 98. A panel must also be replaced when there are too many previous repairs in a given section or area. In aircraft construction, a panel is any single sheet of metal covering. A panel section is the part of a panel between adjacent stringers and bulkheads. Where a section of skin is damaged to such an extent that it is impossible to install a standard skin repair, a special type of repair is necessary. The particular type of repair required depends on whether the damage is reparable outside the member, inside the member, or to the edges of the panel. Outside the member. For damage that, after being trimmed, has 81/2 rivet diameters or more of material, extend the patch to include the manufacturer's row of rivets and add an extra row inside the members. Inside the member. For damage that, after being trimmed, has less than 81/2 manufacturer's rivet diameters of material inside the members, use a patch that extends over the members and an extra row of rivets along the outside of the members. Edges of the panel. For damage that extends to the edge of a panel, use only one row of rivets along the panel edge, unless the manufacturer used more than one row. End of page 4 to 99. The repair procedure for the other edges of the damage follows the previously explained methods. The procedures for making all three types of panel repairs are similar. Trim out the damaged portion to the allowances mentioned in the preceding paragraphs. For relief of stresses at the corners of the trim out, round them to a minimum radius of 1/2 inch. Lay out the new rivet row with a transverse pitch of approximately 5 rivet diameters and stagger the rivets with those put in by the manufacturer. Cut the patch plate from material of the same thickness as the original or the next greater thickness, allowing an edge distance of 21/2 rivet diameters. At the corners, strike arcs having the radius equal to the edge distance. Chamfer the edges of the patch plate for a 45 degrees angle and form the plate to fit the contour of the original structure. Turn the edges downward slightly so that the edges fit closely. Place the patch plate in its correct position, drill one rivet hole, and temporarily fasten the plate in place with a fastener. Using a hole finder, locate the position of a second hole, drill it, and insert a second fastener. Then, from the back side and through the original holes, locate and drill the remaining holes. Remove the burrs from the rivet holes and apply corrosion protective material to the contacting surfaces before riveting the patch into place. Repair of lightning holes. As discussed earlier, lightning holes are cut in rib sections, fuselage frames, and other structural parts to reduce the weight of the part. The holes are flanged to make the web stiffer. Cracks can develop around flanged lightning holes, and these cracks need to be repaired with a repair plate. The damaged area, crack, needs to be stop drilled or the damage must be removed. The repair plate is made of the same material and thickness as the damaged part. Rivets are the same as in surrounding structure and the minimum edge distance is 2 times the diameter and spacing is between 4 to 6 times the diameter. Figure 4, 181. Illustrates a typical lightning hole repair. Repairs to a pressurized area. The skin of aircraft that are pressurized during flight is highly stressed. The pressurization cycles apply loads to the skin, and the repairs to this type of structure requires more rivets than a repair to a non-pressurized skin. Figure 4, 182. End of page 4 to 100. 1. Remove the damaged skin section. 2. Radius all corners to 0.5 inch. 3. Fabricate a doubler of the same type of material as, but of one size greater thickness than, the skin. The size of the doubler depends on the number of rows, edge distance, and rivet spacing. 4. Fabricate an insert of the same material and same thickness as the damaged skin. The skin to insert clearance is typically 0.015 inch to 0.035 inch. 5. Drill the holes through the doubler, insertion, and original skin. 6. Spread a thin layer of sealant on the doubler and secure the doubler to the skin with clacos. 7. Use the same type of fastener as in the surrounding area, and install the doubler to the skin and the insertion to the doubler. Dip all fasteners in the sealant before installation. Stringer repair. The fuselage stringers extend from the nose of the aircraft to the tail, and the wing stringers extend from the fuselage to the wingtip. Surface control stringers usually extend the length of the control surface. The skin of the fuselage, wing, or control surface is riveted to stringers. Stringers may be damaged by vibration, corrosion, or collision. Because stringers are made in many different shapes, repair procedures differ. The repair may require the use of preformed or extruded repair material, or it may require material formed by the airframe technician. Some repairs may need both kinds of repair material. When repairing a stringer, first determine the extent of the damage and remove the rivets from the surrounding area. Figure 4, 183. Then, remove the damaged area by using a hacksaw, keyhole saw, drill, or file. In most cases, a stringer repair requires the use of insert and splice angle. When locating the splice angle on the stringer during repair, be sure to consult the applicable structural repair manual for the repair piece's position. Some stringers are repaired by placing the splice angle on the inside, whereas others are repaired by placing it on the outside. End of page 4 to 101. Extrusions in preformed materials are commonly used to repair angles and insertions or fillers. If repair angles and fillers must be formed from flat sheet stock, use the brake. It may be necessary to use bend allowance and sight lines when making the layout in bends for these formed parts. For repairs to curved stringers, make the repair parts so that they fit the original contour. Figure 4, 184 shows a stringer repair by patching. This repair is permissible when the damage does not exceed 2/3 of the width of one leg and is not more than 12 inches long. Damage exceeding these limits can be repaired by one of the following methods. Figure 4, 185 illustrates repair by insertion where damage exceeds 2/3 of the width of one leg and after a portion of the stringer is removed. Figure 4, 186 shows repair by insertion when the damage affects only one stringer and exceeds 12 inches in length. Figure 4, 187 illustrates repair by an insertion when damage affects more than one stringer. Former or bulkhead repair. Bulkheads are the oval-shaped members of the fuselage that give form to and maintain the shape of the structure. Bulkheads or formers are often called forming rings, body frames, circumferential rings, belt frames, and other similar names. They are designed to carry concentrated stress loads. There are various types of bulkheads. The most common type is a curved channel formed from sheet stock with stiffeners added. Others have a web made from sheet stock with extruded angles riveted in place as stiffeners and flanges. Most of these members are made from aluminum alloy. Corrosion-resistant steel formers are used in areas that are exposed to high temperatures. Bulkhead damages are classified in the same manner as other damages. Specifications for each type of damage are established by the manufacturer and specific information is given in the Maintenance Manual or SRM for the aircraft. Bulkheads are identified with station numbers that are very helpful in locating repair information. End of page 4 to 102. Figure 4, 188 is an example of a typical repair for a former, frame section, or bulkhead repair. 1. Stop drill the crack ends with a number 40 size drill. 2. Fabricate a doubler of the same material but one size thicker than the part being repaired. The doubler should be of a size large enough to accommodate 1/8-inch rivet holes spaced 1 inch apart, with a minimum edge distance of 0.30 inch and 0.50 inch spacing between staggered rows. Figure 4, 189. 3. Attach the doubler to the part with clamps and drill holes. 4. Install rivets. Most repairs to bulkheads are made from flat sheet stock if spare parts are not available. When fabricating the repair from flat sheet, remember the substitute material must provide cross-sectional tensile, compressive, shear, and bearing strength equal to the original material. Never substitute material that is thinner or has a cross-sectional area less than the original material. Curved repair parts made from flat sheet must be in the zero condition before forming, and then must be heat-treated before installation. Long-run repair. Generally, longerons are comparatively heavy members that serve approximately the same function as stringers. Consequently, long-run repair is similar to stringer repair. Because the long-run is a heavy member and more strength is needed than with a stringer, heavy rivets are used in the repair. Sometimes bolts are used to install a long-run repair. Due to the need for greater accuracy, they are not as suitable as rivets. Also, bolts require more time for installation. If the long run consists of a formed section and an extruded angle section, consider each section separately. A long run repair is similar to a stringer repair, but keep the rivet pitch between 4 and 6 rivet diameters. If bolts are used, drill the bolt holes for a light drive fit. Spar repair. The spar is the main supporting member of the wing. Other components may also have supporting members called spars that serve the same function as the spar does in the wing. Think of spars as the hub, or base, of the section in which they are located, even though they are not in the center. End of page 4 to 103. The spar is usually the first member located during the construction of the section, and the other components are fastened directly or indirectly to it. Because of the load the spar carries, it is very important that particular care be taken when repairing this member to ensure the original strength of the structure is not impaired. The spar is constructed so that two general classes of repairs, web repairs and cap strip repairs, are usually necessary. Figures 4, 189 and 4 to 190 are examples of typical spar repairs. The damage to the spar web can be repaired with a round or rectangular doubler. Damage smaller than 1 inch is typically repaired with a round doubler, and larger damage is repaired with a rectangular doubler. 1. Remove the damage and radius all corners to 0.5 inch. 2. Fabricate doubler, use same material and thickness. The doubler size depends on edge distance, minimum of 2D, and rivet spacing, 4-6D. 3. Drill through the doubler and the original skin and secure doubler with clecos. 4. Install rivets. Rib and web repair. Web repairs can be classified into two types. 1. Those made to web sections considered critical, such as those in the wing ribs. 2. Those considered less critical, such as those in elevators, rudders, flaps, and the like. End of page 4 to 104. Web sections must be repaired in such a way that the original strength of the member is restored. In the construction of a member using a web, the web member is usually a light gauge aluminum alloy sheet forming the principal depth of the member. The web is bounded by heavy aluminum alloy extrusions known as cap strips. These extrusions carry the loads caused by bending and also provide a foundation for attaching the skin. The web may be stiffened by stamped beads, formed angles, or extruded sections riveted at regular intervals along the web. The stamped beads are a part of the web itself and are stamped in when the web is made. Stiffeners help to withstand the compressive loads exerted upon the critically stressed web members. Often, ribs are formed by stamping the entire piece from sheet stock. That is, the rib lacks a cap strip, but does have a flange around the entire piece, plus lightning holes in the web of the rib. Ribs may be formed with stamped beads for stiffeners, or they may have extruded angles riveted on the web for stiffeners. Most damages involve two or more members, but only one member may be damaged and need repairing. Generally, if the web is damaged, cleaning out the damaged area and installing a patch plate are all that is required. The patch plate should be of sufficient size to ensure room for at least 2 rows of rivets around the perimeter of the damage that includes proper edge distance, pitch, and transverse pitch for the rivets. The patch plate should be of material having the same thickness and composition as the original member. If any forming is necessary when making the patch plate, such as fitting the contour of a lightning hole, use material in the zero condition and then heat treat it after forming. Damage to ribs and webs that requires a repair larger than a simple plate probably needs a patch plate, splice plates, or angles and an insertion. Figure 4, 191. Leading edge repair. The leading edge is the front section of a wing, stabilizer, or other airfoil. The purpose of the leading edge is to streamline the forward section of the wings or control surfaces to ensure effective airflow. The space within the leading edge is sometimes used to store fuel. This space may also house extra equipment, such as landing lights, plumbing lines, or thermal anti-icing systems. The construction of the leading edge section varies with the type of aircraft. Generally, it consists of cap strips, nose ribs, stringers, and skin. The cap strips are the main lengthwise extrusions, and they stiffen the leading edges and furnish a base for the nose ribs and skin. They also fasten the leading edge to the front spar. The nose ribs are stamped from aluminum alloy sheet or machined parts. These ribs are U-shaped and may have their web sections stiffened. Regardless of their design, their purpose is to give contour to the leading edge. Stiffeners are used to stiffen the leading edge and supply a base for fastening the nose skin. When fastening the nose skin, use only flush rivets. Leading edges constructed with thermal anti-icing systems consist of 2 layers of skin separated by a thin airspace. The inner skin, sometimes corrugated for strength, is perforated to conduct the hot air to the nose skin for anti-icing purposes. Damage can be caused by contact with other objects, namely, pebbles, birds, and hail. However, the major cause of damage is carelessness while the aircraft is on the ground. End of page 4 to 105. A damaged leading edge usually involves several structural parts. FOD probably involves the nose skin, nose ribs, stringers, and possibly the cap strip. Damage involving all of these members necessitates installing an access door to make the repair possible. First, the damaged area has to be removed and repair procedures established. The repair needs insertions and splice pieces. If the damage is serious enough, it may require repair of the cap strip and stringer, a new nose rib, and a skin panel. When repairing a leading edge, follow the procedures prescribed in the appropriate repair manual for this type of repair. Figure 4, 192. Repairs to leading edges are more difficult to accomplish than repairs to flat and straight structures because the repair parts need to be formed to fit the existing structure. Trailing edge repair. A trailing edge is the rearmost part of an airfoil found on the wings, ailerons, rudders, elevators, and stabilizers. It is usually a metal strip that forms the shape of the edge by tying the ends of a rib section together and joining the upper and lower skins. Trailing edges are not structural members, but they are considered to be highly stressed in all cases. Damage to a trailing edge may be limited to one point or extended over the entire length between two or more rib sections. Besides damage resulting from collision and careless handling, corrosion damage is often present. End of page 4 to 106. Figure 4, 190. Wing spar repair. Figure 4, 191. Wing rib repair. End of page 4 to 107. Trailing edges are particularly subject to corrosion because moisture collects or is trapped in them. Thoroughly inspect the damaged area before starting repairs, and determine the extent of damage, the type of repair required, and the manner in which the repair should be performed. When making trailing edge repairs, remember that the repaired area must have the same contour and be made of material with the same composition and temper as the original section. The repair must also be made to retain the design characteristics of the airfoil. Figure 4, 193. Specialized repairs. Figures 4, 194 through 4 to 198 are examples of repairs for various structural members. Specific dimensions are not included since the illustrations are intended to present the basic design philosophy of general repairs rather than be used as repair guidelines for actual structures. Remember to consult the SRM for specific aircraft to obtain the maximum allowable damage that may be repaired and the suggested method for accomplishing the repair. Inspection openings. If it is permitted by the applicable aircraft maintenance manual, installation of a flush access door for inspection purposes sometimes makes it easier to repair the internal structure as well as damage to the skin in certain areas. This installation consists of a doubler and a stressed cover plate. A single row of nut plates is riveted to the doubler, and the doubler is riveted to the skin with two staggered rows of rivets. Figure 4, 199. The cover plate is then attached to the doubler with machine screws. End of page 4 to 108. Figure 4, 193. Trailing edge repair. End of page 4 to 109. Figure 4, 194. C-channel repair. End of page 4 to 110. Figure 4, 195. Primary Z-section repair. End of page 4 to 111. Figure 4, 196. U-channel repair. End of page 4 to 112. Figure 4, 197. Channel repair by patching. Figure 4, 198. Channel repair by insertion. End of page 4 to 113. Figure 4, 199. Inspection hole. End of page 4 to 114. End of chapter 4.